Welcome, everyone. I'm Greg Ristabin from Olympus NDT. I'd like to welcome everyone to this webinar entitled OmniScan MX2 for Corrosion Mapping and Position C-Scan. This webinar will give the participant demonstrations and explanations of a 1D linear array probe optimized for corrosion mapping and similar applications using the Position C-Scan on the OmniScan MX2. Our presenter today is Chris Magruder. Chris is the Phased Array AUT Manager for Olympus and has been developing and delivering phased array systems for over 12 years. This webinar is budgeted for about 60 minutes. Its main presentation should last probably that long, leaving minimal time for questions. If you do have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of the presentation. Do not type your questions into the chat panel, as we do not monitor chat for Q&A purposes. Alternatively, you may send an email to phasedarraysupport@olympusndt.com for any more information that you may want or any questions that you may have. And that address is on that first screen that you're seeing right now. If we don't get you your questions during the webinar, they will be addressed personally either by email or by phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, it's all yours.
Good afternoon, everybody, or good morning or evening, wherever you're at. Thanks for joining us. Like Greg had said, my name's Chris Magruder. I'm going to be explaining today some of the ABCs of how to set up the OmniScan MX2 for a corrosion mapping inspection using a typical 1D linear array probe. The setup you see here is generally where most of the data and screenshots have been taken from. The data files, in addition to the presentation, is going to be made available from a link from the email, and this is an abridged version of the MX2 training program chapters for corrosion. So the instrument module we're going to be using, and that was used to acquire the data today, is a new PA2 module designed to be used with MX2. It has a slightly different connector, simultaneous LEMO UT board with the phased array, and this application requires a single group with one probe, so it can be done with any number of modules. The minimum requirement would be a 1664 or up. The wedge associated with these are either a specialized water wedge or corrosion wedge, which you'll see some later in the presentation, or a 0-degree linear wedge. So for the probes in the catalog, in all of the corrosion probes we're going to be using are typically 5 to 7 megahertz and a large element count. 60 or 64 elements are typical. The associated wedge for each family, and in this example in the graphic, is an A2 family probe with the associated wedge. So you'll see any family housing of probes has their associated 0-degree L-wave wedge in the catalog. These differ in frequency and pitch, so coverage and accessibility is our primary concern. We want the individual beam quality of a small UT probe multiplexed across a wide array for coverage and better imaging. The software needs to know a lot about the wedge to be able to form the beams correctly. Wedges account for the overwhelming amount of our support issues due to the phased array not performing like the customer intends. It's not automatically detected by the software, obviously, so it must be selected from the database. In the OmniScan setup wizard, when you get to the probe wedge part, we can see the probe was automatically detected with auto on and all of the various parameters entered. What the software needs to know about the wedge is the model, the height of the first element, the relationship of element 1 to the bottom of the wedge, called the height, in this case 20 millimeters. A 20 millimeter wedge of rexolite velocity is designed to put a surface interface multiple, or the wedge reflection, in carbon steel about 50 millimeters. So with this wedge in carbon steel, I can go from 0 to 50 millimeters without any obstructions from the second wedge echo. And these wedges come in different standoffs for moving that interference around strategically. The software needs to know the angle. Obviously, this is at 0 degrees, and not related to the focal laws, but the relationship of the first element to the face of the wedge, always referenced in a negative number. The element 1 is minus 56 millimeters away from the wedge. So beam 1 under element 1, center point, will be our 0, 0 position on the C-scan. If the offsets are not correct, the C-scan won't represent what you're looking at in the material. After the probe and the wedge are entered into the step-by-step wizard of the MX2, we're going to enter the focal law wizard and select linear at 0 mode. This is one of 3 group modes that manages focal laws and has an effect on how the C-scan is displayed. In our typical angular sector scan, this axis of the C-scan is a focal law axis, meaning focal law 1 through focal law last. What the linear at 0 mode does is allow beam-to-beam center point referenced correctly on the C-scan, or a merge of the data that's not possible on the instrument at an angle. So one of the limitations of the easier to use linear at 0 is it only allows one group. But within the 1 or 2 axis encoder, there are many advantages to this, both in an immersion tank or composite inspection application and in corrosion mapping. The focal laws are entered directly into the calculator, either through the NDT setup builder that we'll see in a minute, or in the OmniScan user interface. We're going to see a graphic that explains this, but the element quantity is directly relevant to the size of the probe. In conventional UT, we call that diameter or size. So if I'm using the 0.6 element probe with an aperture of 12 elements, I'm essentially creating the beam equivalent of a pulse echo 5 megahertz 7.2 millimeter probe. I'm going to start on the first element for focal law 1, and I want focal law last to terminate on element 64 with a 1 element step. So I'm going to step away from the presentation for a moment, and we're going to look at this same setup in an application or a program called the NDT Setup Builder. The Setup Builder software is designed to be a calculator with ray tracing capabilities for simple geometries. The instrument or acquisition unit is entered to tell the focal law calculator the limits of our active pulsars and total elements in the probe and UT channels. Once this is entered, the software isn't going to allow me to create a condition that's not compatible with the instrument I'm using. So the part is very simple for a corrosion or time of flight type of inspection, and I only need to enter velocity of the material, selecting from the database, and a thickness for the component. This is strictly for plotting dimensions of the probe and the beam coverage. So the component's configured, and the rest of this we can do directly from the Add Probe tab. When we add the probe, we select from a PA linear, Toft, a UT probe, or a dual matrix array. The probe series and model is entered. The associated wedge series and model is entered. The position is relevant to the beam angle. So generally for all of our corrosion or 0-degree linear scans, we're going to be at a default skew of 90 degrees of the component. So once the probe, wedge, and material are entered, and again, here's the material, here's our wedge, the same one we looked at in the presentation, and the elements. This is element 1, and this is element 64. And as you can see, the A2 probe is asymmetrical in the housing, meaning that there's empty space in the housing on this side. So it becomes relative which side of the probe you're using for the inspection. Some of the same models of A2 probes, such as the 2 megahertz version, are symmetrical in the housing family. So we go to groups to form our beams. We select a new line here by adding either a group to any active probe. We're going to select a linear scan, which is defined by the same focal law multiplexed across the entire probe, whereas a sector scan would be a series of different focal laws from the same elements within a probe. We select the longitudinal wave velocity, the angle of 0 degrees, the start position of the first element. So the software is asking us to find the first element of the first focal law, and we're going to use the entire probe for element 1 and the last focal law of the beam coverage, and we'll use all 64 elements. We're going to use an aperture of 12 elements grouped together. So focal law 1, or A-scan 1, that you see here is using elements 1 through 12. Focal law 2, element 2 through 13. That happens all the way across the probe until focal law last, using elements 53 to 64. So the total coverage is visible, and it gives us about 33 millimeters of total probe coverage, with each A-scan being a direct equivalent of a pulse echo 5 megahertz 7 millimeter probe. So we should expect very good flaw characterization and detection looking at the C-scan and S-scan data from the setup. So this is our basic setup now. With the linear mode, we only have one group available. This group can be directly exported to a file called a connectivity file that allows it to be put on the flash card of the instrument and imported directly. It can be generated as a law file, similar to the calculators like the TomoView calculator, or you can quickly copy this and create the same setup using the OmniScan MX2 wizard. As far as the phased array goes, compared to conventional UT or phased array angle beam weld inspection, amplitude-based, it's fairly simple. It's an entry-level application. So coming back to our presentation, This is what would generate the same beam information using the OmniScan wizard. On the display, a grouping of 12 elements using all 64 elements on the probe gives us an exact coverage of 31.8 millimeters. Focal law 1 is here. Focal law last is here. And the lines of data on this axis are created by the probe movement over the component, either with a clock inspection or an encoder. The S-scan display represents focal law 1 here at this edge, and focal law last here, 64. So at any given time, we have a window of about 31 millimeters directly under the probe where we're seeing every A-scan summed. As I move this blue cursor here, I can see the A-scan that generated that data point with a 1-element step resolution. When the step resolution is increased to 2, the data file is 1/2 the size. The acquisition speed of the scanner is double, although we don't typically consider this application a speed application that would push the limits of the PRF, like multi-group weld inspection. And if we have a probe that has a 1 millimeter pitch, or a point, in this case, a 0.6 millimeter pitch, how do we step the beam resolution smaller than the pitch of the probe? We do that by entering a 0.5 element step resolution. This is a way of creating a smaller focal law of 1 less element in between every other focal law for improved resolution, improved defect characterization, and ability to detect small pits much better than the 1-step resolution. The downside is the file size will double, twice as much information. The speed of the max PRF is also cut in half because of the extra focal laws. But the details of the data are very much improved. We have twice as much resolution inside this defect area here than we do here. Continuing on to the UT configuration. The UT settings regarding point quantity are very relevant for the corrosion inspection, much more so than the amplitude-based weld inspection. The default point value of 320 assigns the resolution inside the A-scan digitized range. If I were to take the total range here of maybe 35 millimeters and divide it by the number of points in the A-scan resolution, it would give me the minimum accuracy of the thickness reading. Often in corrosion mapping, that's defined by the procedure. In some cases, 0.1 millimeter would be the minimum resolution required for some of the corrosion mapping. So you need to be ensured that your point quantity is sufficient enough to meet that resolution on the data. By setting your range appropriately, not excessively long, not excessively short, over your area of interest, and by adjusting the point quantity appropriately, you can be sure to be in compliance with the minimum accuracy. In weld inspection, through use of what's called compression, we will never lose amplitude information. We will lose A-scan characterization or resolution. So it's much more important, this point quantity, when we talk about thickness readings and time of flight inspections or TOFT inspection than the amplitude-based. And this point quantity also is directly relevant to file size and scanner speed, although that's not typically a concern in single group corrosion mapping. The gate configuration, and shortly we're going to take a look at this live on the instrument through the webinar tool. We're just providing a little background. The newer versions of the OmniScan software contain 5 different options for gate configuration. If you're using an older version of the software with only 2, you will benefit enormously for this application by upgrading. In amplitude-based weld inspection, we generally use either the first or highest amplitude peak to generate our C-scan and color palette. In the corrosion mapping, the applicable readings are the first leading, first peak, and max peak points. And for the most part, we generally use A. All of them are available, and some of them have unique applications that make one more advantageous than the other. And those are available under the gate mode that you see here, under the gate menu. And the mode is also available in the applicable readings. I can tell by looking at this reading, I'm looking at the first edge, first peak, leading edge measure mode. So it's important to the thickness reading that we always know what that mode is. And this is identical for gates A and B. The I gate or yellow gate has a little bit different functionality. The gate configuration under the gate menu also must be set for the thickness source. We're going to set a default value for the inspection when we acquire data, and this parameter can be changed in analysis mode or at any time after the inspection in OmniPC or the instrument. In this example, the thickness reading here, 4.48, is taking the signal in gate B, green, minus the signal in gate A. That would remove any paint coating from the thickness reading. Where the interface signal here that we see, this is the wedge to pipe interface signal, can also generate instability and inaccurate readings. So if we were to use the reading, the signal in gate A minus the signal in gate I, any fluctuation between the probe and the surface, and this is especially important in a water wedge like the hydroform or an immersion tank, can be removed from the thickness reading. All combinations for leading edge and peaks can be manipulated for gates A, red, B, green, and gate I, or the interface gate, yellow. So we're going to transition again back to my desktop for a moment and back to a live instrument that we see here. This is set up with the same configuration that we talked about, and going through the UT setup. Okay. Under the wizard, the part and weld wizard is completed in this application only relevant for the thickness of the material being inspected. No weld is used in this application. When we set the thickness and the velocity and the component under the part and weld, this is relevant to all groups. The setup is relative to individual groups. So under our UT settings, for the corrosion inspection, and especially if you're using a water wedge, sometimes it's beneficial to set the range before 0 so I can see the surface interface signal. I want this wedge to component interface signal as small as possible. Higher frequency probes assist in this. Smaller aperture assists in this. And most importantly, a water wedge. One of the big benefits to a water wedge, like the hydroform or an immersion tank or some other custom wedge, is that the interface signal compared to a wedge is fairly small. In this case, up into about 1 or 1.5 millimeters, I have a very good detection on the interface. So my ability to detect very small defects near the surface or pitting or even corrosion right up to the surface is enhanced by a small interface signal. This is a back wall reflection 1 that I have a red gate positioned, and back wall reflection 2 with a green gate. I can reposition these gates as necessary in analysis mode. So I'm going to increase the range slightly so that we can see the wedge interface signal. In this case, here is the wedge, back wall 1, the interface, back wall 1, back wall 2, and this is the wedge echo. The size of your wedge will determine where the wedge echo appears, and the wedge velocity is typically different than the component. So if I remove the wedge from the component and hold the probe freely in the air, I can see that my wedge echo is coming in at about 22 millimeters. So I'm well outside of my range for 2 good back walls. Moving the probe slightly, I can see into the corrosion. So my gate logic, to obtain the correct reading, I'm going to go to the gate menu, and under the A gate mode, I'm going to be pulse on max peak of leading edge. Now we're on first peak of leading edge. First peak of leading edge for all of the readings. And this reading now on the interface gate, normally the mode is in an A-scan synchro or pulse. In this mode, the yellow gate is visible and it's positioned over the interface signal. If I change this to synchronization on I gate, it means that the A-scan 0 position here is automatically dynamically adjusted to the crossing position of the gate. So when I'm moving a big probe with a water wedge over a rough surface, I can ensure that my surface interface signal here is always at 0. That's also called a floating gate in an immersion tank applications. Similar to the I gate, gate A or B can be a floating gate based on the position, in this case 3 millimeters, starting at the interface gate. In the mode we're in now, 3 millimeters equals 3 millimeters on the scale. If I'm in a floating gate for gate A, that gate dynamically floats 3 millimeters from the interface signal. Those are traditionally immersion tank or water corrosion system features that are available for all types of applications, including this one. So in addition to the gate position and gate mode, we also have a specific thickness configuration under the gate menu. It requires a source for the reading, and it requires a thickness range that we see here. The thickness range, and I'm looking at a 10 millimeter component. So naturally, the thickness on the high end is 10 millimeters. Thickness on the low end, we set at 2 millimeters. And normally you don't know this before the inspection. So we'll adjust this as necessary. So what this range does, it determines the minimum reading that can be available that's available for the statistical readings. This is not going to allow any number to appear that does not fall within this range. And as part of our analysis after the inspection, we're going to look at the low spots, look at anomalies and missed data points, and determine where the real value is so that we can adjust the software for our statistical readings that don't interfere with the inspection from missed data points or anomalies and an invalid reading. So more to come on this shortly. And again, both of these, including the source of the reading, can be adjusted anytime after the inspection since we're saving the full A-scan. And again, in the A-I, the 655 is a result of the leading edge of gate A here subtracted from the leading edge of gate I here. So it's very important that we understand our options and make sure we know what we're looking at, because it can have effect of the reading that would put this out of tolerance with the procedure. So we set up the range on the gate thickness for our statistics. And we have another range that we need to enter for the color palette of the C-scan. Normally, this C-scan reflects amplitude. In a weld inspection, it's very typical. So when we change the C-scan from an amplitude, reading the information here, to a time of flight or depth, it's going to read the information here. Amplitude has no bearing on the signal, only position. And position or thickness is correlated to color on the same scale. We establish the scale from 2 to 10 millimeters, and inside of that scale, we can further adjust our color palette for max contrast. We often set the two up the same to acquire the data, and we will manipulate both of them in analysis mode. So, like the wedge, we're also going to select the readings that we want from the database. The OmniScan MX2 has two groups of 4 readings each. They can be configured independently from any of the many readings in the instrument. There's also preset groups already configured for the 8 readings relative to particular applications: Toft, clock corrosion, encoded corrosion, C-scan, manual weld, and so forth. Generally, group 1 or 2 is going to meet the needs of the overwhelming majority of those applications. The readings that are set up in acquisition are passed to the data file So if you configure them correctly in the beginning, you won't have to reconfigure them for every single analysis file. So we're going to talk about a clock acquisition first. Once the UT is set up, the gate is configured, and the color palette for the C-scan, it's simply a matter of acquiring the data. When we hit the start button on the instrument, this C-scan will start to grow or start to acquire data as I move the probe. Without an encoder, there's no direct relationship between the data and the position of the probe. But the characterization, thickness, and where you find the thin spots are very relevant and the point of the inspection. When we're in a clock acquisition, meaning the C-scan is building at the speed of the pulsar, not at the speed of the encoder, we can see a clock inspection icon in the upper left-hand corner. And as you can see, we can adjust both the speed and total size of the C-scan regarding how many data points we will accumulate by adjusting the step resolution, or the PRF, and the total size of the C-scan. The bigger number you put in here, the more data points will be saved. Only the visible part of the C-scan, not the buffered part that's not visible, is retained in the clock data file. So back to the desktop and live on the instrument. Those parameters regarding the C-scan can be found under the Scan menu here. For a one-line scan, meaning that we're not going to be building individual lines together with a two-axis or manual one-axis scanner, it's simply the width under the probe. The time C-scan on the clock will move at about 30 millimeters per second. The area that we enter here is going to give us the total size of the data points we'll retain on the clock inspection, and we can name our data file prior to running the inspection, so all we'll need to do is hit the Save Data button to acquire the data. The new version 4.0 of the software has quick transitions between full screen mode, now where we can still see the readings in full screen mode. It allows the different layouts to be selectable from the touch screen or a mouse directly from full screen mode. And it also allows both readings to be modified and indications added to the indication table while in full screen mode, and a quick way to return to normal screen mode. Those are available from the mouse clicks, the touch screen, or from the function key up and down arrow on the outside of the instrument. Use of an encoder is done with either a 1 or 2 axis encoder to record the data. They come in all shapes and sizes, both from Olympus and from third-party manufacturers. Some of them are built directly into a scanner, like you see here. Some are detachable and can be configured in a number of different positions and ways. All of them basically do the same thing. As the probe or scanner is moved, the encoder is firing all of the focal laws at the speed of the movement. So there's a one-to-one relationship between the C-scan position and the C-scan data. And measuring flaws is then both possible in the scan and index axes. Both 1 and 2 axis encoders are interfaced with the MX2 from an IP66 pigtail that connects to a standard 15-pin connector. To build an interface for any encoder not purchased from Olympus is fairly simple. You need only the 15-pin connector and the pin out for the encoder inputs that can be found in the manual of the OmniScan. But any encoder purchased from Olympus obviously comes pre-configured and simply needs to be plugged in. So on a one-line scan with an encoded inspection, this axis represents the virtual probe or the individual A scans within the probe. Focal law 1 here, referencing elements 1 through 12. Focal law last here, representing up to element 64. Depending on the aperture selected for each A scan, a 1 millimeter pitch probe like this gives us approximately a 50 millimeter footprint that you see here. This axis represents the mechanical movement of the encoder. I can move the encoder backward and forward to rewrite the data if I have a coupling problem or a missed data point because of probe stability. This results in a 1 millimeter by 1 millimeter point density in the C-scan for good coverage and characterization and ability to detect both flat-bottomed holes for the qualification and small pitting for the inspection. When in clock mode, we will see a clock encoder symbol at the top of the instrument. And again, selection of our modes here under the Scan Inspection menu. Options are clock, encoder 1 or 2. The encoder is either calibrated using the wizard or entered the resolution directly from written spec or the instrument itself and verified. When in an encoded inspection, the C-scan is defined by 0 to the scan length. Anytime you are outside the patch defined in the C-scan, if the encoder is not inside of that patch, it will turn red and no data is acquired. Resetting the encoder to 0 or moving it into the patch will allow data to be accumulated in the C-scan and recorded. And in this case, we're starting at 0, referencing here, going to 400 at a 1 millimeter resolution. This is possible up to the file size of 300 megabytes for the MX2. The software won't allow you to create a C-scan patch larger than the maximum file size that can be stored on the MX2. So in a clock, similar to a clock acquisition with the encoder, we will start the inspection here, 0 the C-scan, and start moving and building the C-scan as we go. 2-axis encoded scanners allow a raster scan or an XY pattern to be generated for the data, a much larger coverage. They come in all shapes and sizes, both from Olympus and from third-party manufacturers. Simply selecting the 2 axes enables the raster scan, and we can see here that multiple line scans are used to build the C-scan, whether from an automated scanner or a manual scanner that's being manually manipulated. The C-scan is built with multiple line scans put together. This representing the encoder axis of the scan, always blue. This representing the internal resolution of the whole aperture of all focal laws within the group. In this case, we see three strokes. Stroke 1, stroke 2, coming back the other direction, and stroke 3. And this is called a raster scan. Anytime the raster scan is selected, it's necessary to populate both encoder and encoder 1 for their relative resolutions and encoder preset positions. The linear at 0 mode that we used for the focal law creation has a unique benefit that it automatically calculates the probe aperture resolution, meaning that in this case, with an 8-element A-scan or focal law, using the entire 64-element probes, beam center point 1 through beam center point last gives me a coverage of 33.86 millimeters. Setting the number of strokes for stroke 1 at 0, stroke 2 at 33 millimeters, and stroke 3 as pictured here at 67 dramatically simplifies the programmation of the focal laws, reconciling it with the indexing of the scanner. Again, the linear 0 mode is automatically calculating the resolution for the raster scan of the inspection. So this raster scan can also be accomplished by use of a clicker. Clicking this button one time, even though this is a one-axis scanner, indexes the scanner over one stroke. It's a common method for acquiring multiple line C-scan quickly and easily without having a large, complicated two-axis scanner to manipulate. The T-min reading is the reading that's displayed within the range we set here for the entire C-scan patch. It won't allow any reading to be less than the value entered here and can be adjusted in analysis mode. The color palette is slowly adjusted to provide maximum contrast on the C-scan. From our default position of 2 to 20 millimeters, we can see the full range of our expected thicknesses. Once the data is acquired, we're going to start reducing it slowly. This was how we acquired the data at 2. As I change the minimum value of the color palette, the full range of the color is scaled across the C-scan. We increase it slowly until our first red pixel is present. Once the red pixel is present, we crosshair the data cursors there, and we can see the S-scan and the associated A-scan that represent the lowest reading. It's normal in severely corroded inspections that there would be some missed data points due to a no detection gate. The overall fitness for service or river bottom of the component can be seen directly in the data, and the gate readjusted if necessary to help improve the missed data pixels. In this case, a missed data point is a pixel white as a result of a short gate that can be increased to include the real defect that you see here. We can see it in the S-scan and it was not detected in the C-scan because of a gate position. In this instance, a red pixel was generated erroneously because the gate was too close to the surface interface signal here. So we moved the gate slightly to get the good C-scan image. The reading source is changed appropriately. Here's our water, surface interface, and back wall. The readings are changed for either the entire C-scan, which would be the T reading, or any reading with the zone, which would be a box within the cursors. In this case, we're looking at the entire C-scan thickness and the thickness reading of the data point crosshairs. Material loss is determined based on the thickness entered per the component. In this reading here of 3.7 millimeters, it is 58.9% loss from the 9 millimeter component. The T-min reading, again, the entire C-scan. The T-min zone reading is a zone within the crosshairs of the reference cursor and measure cursor. So within this zone, designated by a Z, I see the lowest reading, and both the T-min and T-min zone have associated scan axis position and index axis position for the reading. The indication table is populated exactly like the UT for weld inspection. We optimize all displays, cursors, and display the relative reading representative of the low point, and either from a right click on the title bar or using the menu for the indication table, defects are added to the database and recorded and printed. There were several questions from people that I didn't get to. I apologize about the technical hiccup getting dropped offline briefly. This was an abridged, abbreviated version of the full MX2 corrosion training PowerPoints that everybody participated in the webinar will receive. In the follow-up email to this, it will include the questions I didn't have time to get to during the presentation, and also a copy of the data files that were referenced using OmniPC during the presentation. Again, I want to thank everybody for attending. I look forward to seeing you guys at our next webinar regarding top inspection, and I'll turn this over to Greg Ristabon right now to wrap it up. Greg?
Thank you, everyone, and thanks, Chris, for your participation in today's event. We hope the material presented was informative and useful. Follow-up emails will go out, as Chris said, to all attendees with links to the presentation files and the data files. The webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. That's going to do it for today, and again, thanks to everyone for participating. Keep your eye on our website for more sign-ups for more webinars coming down the pipe. And your follow-up email will also provide links to those follow-up email, to those additional webinars that are coming up in the future. So take care, and thanks for coming today.